Hi, welcome to MicroMechanisms. On this channel, we don't just list diseases or bacteria, we slow down and look at the mechanism, how things actually work inside the body. So today, we're going to look at Yersinia Pestis, and to understand how it causes so much damage. And the key question here is not transmission alone, but why immunity fails first. Let's begin with the human body. Every day, we're exposed to microbes. Most of the time, the immune system detects them quickly, raises alarms, and clears the threat before we ever notice. But in this case, something unusual happens. The pathogen is present, immune cells are nearby, and yet, there is no alarm. This early silence is the key to everything that follows. So, Yersinia pestis doesn't begin in humans. It lives in rodents, and it moves between hosts using fleas. When an infected flea bites a human, the bacteria enter through the skin. Now, once the bacteria are inside, the question becomes, where do they go next? After entering the skin, the bacteria don't spread randomly and are not immediately destroyed. They survive long enough to access local tissue and lymphatic vessels. Through the lymphatic system, Yersinia pestis reaches the lymph nodes. This is significant. Lymph nodes are designed to be immune checkpoints. This is where the infection becomes visible. In the lymph nodes, bacterial numbers increase rapidly. The immune system responds, cells arrive, inflammation builds. From here, two paths are possible. The infection may remain localized, or if immune control fails, the bacteria can enter the bloodstream. And the difference between these two paths is the difference between survival and shock. But despite this response, the infection doesn't stop here. Inside lymph nodes, macrophages and other immune cells attempt containment. This is where early immunity normally wins. But Yersinia pestis does not fight fair. Macrophages attempt to engulf Yersinia pestis, just like they would with most bacteria. At first glance, this looks like a normal immune response, but very quickly, the balance shifts. Because Yersinia pestis isn't passive. It activates a specialized system, the type 3 secretion system. Using this, it injects YOP proteins into immune cells. And rather than killing the cells outright, these proteins disable them. What follows is not immune failure, but immune paralysis. With the immune system delayed and disorganized, the bacteria gain time. They multiply. They escape local control. And gradually they move beyond the lymph nodes and into the bloodstream. Once in the bloodstream, a new mechanism takes over. As a gram-negative bacterium, Yersinia pestis releases endotoxin LPS. This doesn't trigger a focused immune response. Instead, it causes widespread inflammation and vascular effects. And this is where immune evasion turns into systemic collapse. The resulting vasodilation and capillary leak reduce blood pressure. Organs receive less oxygen. This is septic shock. And in some cases, before treatment is possible, the infection reaches the lungs. This summarizes the mechanism clearly. Type 3 secretion leads to weak early inflammation. Weak inflammation allows uncontrolled spread. Uncontrolled spread leads to shock and increased mortality. The disruption of macrophage signaling by the type 3 secretion system is the central event driving plague pathogenesis. But today, with antibiotics and surveillance, plague is no longer the threat it once was. Still, the mechanism remains important. Disease isn't just about presence. It's about timing, control, and how small molecular interactions scale into whole body failure. Thanks for watching. This is MicroMechanisms, where we explain how diseases work, not just what they are.